Today, everyone, we the Group 1 will be discussing the law of reflection and polarization, the Malus law. First, I will be discussing the law of reflection. The law of reflection states that the angle of incidence of a wave strike a surface equal the angle of reflection of that wave. It applies to various types of waves including light and sound. In simpler terms, when waves encounter a surface, they bounce back in a way that follows a specific pattern. The angle at which a wave approaches the surface is the same as the angle at which it leaves the surface. This means that if you shine a light beam to a mirror at a certain angle, the reflected light beam will bounce off a mirror at the exact same angle but in opposite direction. The law of reflection applies to smooth and shiny surfaces such as mirrors or still waters. It helps explain why we can see our reflection in a mirror or why light appears to bounce off a calm lake. The law of reflection is a fundamental principle in optics and is used in various applications including the design of mirrors, lenses, and other optical devices. So there are two types of reflection, regular reflection and irregular reflection. Regular reflection, it occurs when all the reflected rays from a given smooth surface are parallel to the parallel incident rays. This occurs from smooth surface like a mirror, silver spoon, and etc. The image is formed and seen, as what you can see on the illustration below. For example, when light waves bounce off a smooth surface like a mirror and follow a specific rule called the law of reflection. This creates a clear and a sharp reflection like when you see yourself in a mirror. The smoothness of the surface is important for regular reflection to happen. For irregular reflection, it occurs when for a given set of parallel incidence rays, the reflected rays do not remain parallel to each other. This occurs from rough surfaces like wood, table, door, book, etc. It helps to see objects. No images or blurry images can be seen, as what you can see under illustration below. So, irregular reflection, also known as a diffuse reflection, this occurs when incident ray bounces off a rough or uneven surfaces. Unlike regular reflection, where the reflected rays remain parallel. In irregular reflection, the rays scatter in different directions. This scattering creates a blurry or scattered reflection. Therefore, regular reflection differ from irregular reflection because regular reflection have a smooth surface and irregular reflection have a rough surface. For the continuation, the incident rays and reflected rays will be discussed by Angelo.
Law of reflection formula given as sin theta I is equals to sin theta r. This is the sin theta I is the angle of incidence while the sin theta r is the angle of reflection. Polarization. Polarization refers to the orientation of oscillations in a transverse wave. When we say transverse wave, it is a wave that vibrates perpendicularly. For example, if light strikes an interface so that there is a 90 degrees angle between the reflected and refracted rays, the reflected light will be linearly polarized. When we say linearly polarized, it is the particles vibrate in a single plane perpendicular to the direction of propagation. The direction of polarization, the way the electric field vector's point is parallel to the plane of the interface. In the given illustration, unpolarized light can also undergo polarization by reflection of non-metallic surfaces. The extent to which polarization occurs is dependent upon the angle at which the light approaches the surface and upon the material that the surface is made of. Metallic surfaces reflect light with a variety of vibrational directions. Such reflected light is unpolarized. However, non-metallic surfaces such as asphalt, roadways, snowfields, and water reflect light such that there is a large concentration of vibrations in a plane parallel to the reflecting surface. When an polarized light strikes a reflecting surface at a specific angle, the reflected light becomes linearly polarized. This occurs because the electric field component perpendicular to the plane of reflection is proportionally reflected, while the parallel component is partially absorbed or transmitted. The angle of polarization, which defines the plane of vibrations for the reflected light, is always perpendicular to the plane of incidence, the plane containing the incident ray, and the normal to the surface.
For the continuation, I will discuss the Malus law. Malus law, named after the French scientist Louis Malus, is a fundamental principle in optics that describes how the intensity of light changes when it interacts with the polarizer. It holds the key to understanding the fascinating world of polarized lights and its many applications. In 1808, using a calcite crystal, Malus discovered that natural incident light became polarized when it was reflected by a glass surface, and that light reflected close to an angle of incidence of 57 degrees could be extinguished when viewed through the crystal. What does Malus' law say? Malus' law states that the intensity, which is the I, of polarized light transmitted through a polarizer is proportional to the square of the cosine of the angle, which is the theta, between the polarization axis of light and the transmission axis of polarizers, and meaning mathematically it can be expressed as intensity cos theta equals to the intensity cos squared theta, where I is the initial intensity of the light and the theta is the angle between the polarization axes. In the given picture, it shows the glass plate, which is an example of calcite crystals that discovered by Malus. This calcite crystal shows the incident light and reflected light. It means that the incident light, this is the light that strikes the surface of the calcite crystals. It can be unpolarized or already polarized in a specific direction. While the reflected light, when light hits the calcite crystals, a portion of it bounces off the surface. This is the reflected light. The angle of reflection is equal to the angle of incidence, following the law of reflection that is already discussed by Ms. Mercedes and Mr. Mapalad. What is polarized light? This polarized light is an ordinary light consists of vibrations in all directions, perpendicular to its path. However, polarized light has its vibration restricted to a single plane. Imagine a rope swinging up and down, but instead of moving in all directions, it's confined to a specific plane. This is analogous to polarized light because polarized light is a special type of light where the direction of oscillation of its electric field is restricted to a specific plane, unlike unpolarized light where the electric field oscillates in all directions perpendicular to the direction of propagation. As what, as what I have said earlier, Malus' law is a fundamental principle in the realm of polarized light because it described the relationship between the intensity of linearly polarized light and its interaction with an analyzer. So some purposes of Malus law because the Malus law quantifies the change in intensity of linearly polarized light as it passes through an analyzer, allowing for precise calculations and measurements. It also determined the polarization by observing the change in intensity with varying analyzer orientation. Malus law helps determine the orientation of the polarization plane of the incident light. It also controls intensity. By controlling the analyzer orientation, Malus law can be used to regulate the intensity of transmitted light, finding application in various optical instruments. As the given below picture, it shows the polarizer, analyzer, and the direction of propagation. And also it contains the intensity of light after passing through the polarizer, and the intensity of light after passing through the analyzer. And also, it is the angle between the axis of the polarizer and the analyzer. This polarizer, this polarizer, imagine a filter that only allows light waves with a specific orientation of their electric field to pass through. This is a polarizer because it acts like a gate for a light, selectively transmitting waves based on their polarized state. Think of a picket fence with horizontal slats. Light waves with horizontally oscillating electric fields can squeeze through the gaps, while those oscillating vertically are black. This is an analogy for how a polarizer works. Second is the analyzer. This analyzer is another filter, similar to a polarizer, but used to analyze the polarization state of incoming light. It essentially acts like a detector, measuring the intensity of light that can pass through its own specific orientation. Imagine another picket fence with a slat at a different angle. By rotating the analyzer, you can control the angle between its slats and the polarization plane of the incoming light, influencing how much light gets through. Next is, or the last, is the direction of propagation in Malus law. Malus law focuses on the interaction between linearly polarized light and the analyzer. The direction of propagation is crucial for understanding this interaction because the incident light, imagine the light traveling in a straight line before encountering the analyzer. This is the incident direction.
Good day, ma'am. We will going to discuss the applications of reflection, refraction, dispersion, and polarization. Reflection is the phenomenon where light bounces back after hitting a surface. It's used in many everyday applications like mirrors, periscopes, and reflective safety clothing. It's also crucial in technologies like telescopes, microscopes, and fiber optics. Reflection is a fundamental concept in physics. It's the change in direction of a wavefront at an interface between two different media so that the wavefront returns into the medium from which it originated. In simpler terms, it's when the light bounces off an object. One of the common example is the mirror. When we look at ourselves in a mirror, we can see a reflection. When the light from our body hits the mirror, it bounces back. That allows us to see our image. Reflection is not just limited to mirrors. It can happen all around us all the time. Example is that it can be any body of water like lake. Reflection has its applications in many areas of life and technologies. For an example is the periscopes or endoscopes that allows the doctors to see the human body, and also the telescopes which are used by the astronomers. Reflection plays a crucial role in physics and has numerous applications that are integral to our daily lives. For an example, in optics, where the cameras, the microscopes, telescopes are used even in our eyes. And it is also used in communication, where it is used in satellites and radar technologies. Also in solar energy, where it captures and concentrate solar energies into electricity, and reflection is also used in several researches or scientific researches. Reflection is one of those important things that makes us alive and kicking.
Refraction is the bending or change in direction of a wave, such as light or sound, as it passes from one medium to another. This occurs because the speed of the wave changes when it enters a different medium, causing it to change direction. The change in direction is due to the change in the wave's velocity, which is determined by the properties of the two media involved. One common example of refraction is the bending of light when it passes from air into water. When a beam of light travels from air, it less dense medium. When it into the water, a more dense medium, it slows down and changes direction. This change in direction is what causes the phenomenon of refraction. For instance, if you place a pencil partially in a glass of water, it appears to be a bend at the water surface. This is because the light rays from the pencil travels through the air and then enter the water at an angle. As the light passes from the air to water, it slows down and changes direction, causing the pencil to appear bent. For example, for a refraction, optics and lens design. Lenses use refraction to converge or diverge light, allowing for the formation of images in cameras, telescopes, microscopes, and eyeglasses. Number 2 example is fiber optics. Fiber optic cables rely on the principle of total internal reflection, a form of refraction, to transmit the data over the long distances. Light signals are sent through thin strands of glass or plastic fibers, which guide the light by repeatedly reflecting it off the walls of the fiber. This technology enables high-speed data transmission in telecommunications, internet connectivity, and other communication systems. Third example is prisms and spectroscopy. Prisms are used to separate white light into its component colors through dispersion, which is a result of refraction. This property is utilized in spectroscopy to analyze the composition of substances based on the unique patterns of light they emit or absorb. Number 4 is the mirage. Mirage are optical illusions caused by the refraction of light in the air's atmospheres. So, hot air near the ground can create variations in air density, causing light to bend and create distorted images. Number 5 is the corrective lenses. Eyeglasses and contact lenses use refraction to correct vision problems such as nearsighted or myopia, farsightedness or hyperopia, and astigmatism by altering the path of light entering the eyes. These lenses help focus light onto the retina, improving vision. Number 6 is the microscopy. Refraction plays a crucial role in microscopy, allowing for the magnification and visualization of tiny objects. Microscopes use lenses to refract light and form enlarged images of microscopic specimens, aiding scientific research, medical diagnostics, and various industrial applications. Number 7, aquariums and fish tanks. The refraction of light at the air-water interface in aquariums and fish tanks can create visually appealing effects. The bending of light can make objects inside a tank appear larger or distorted, enhancing the viewing experiences. These are just the few examples of how refraction is applied in different fields. Refraction's its ability to manipulate the light and its properties has led to numerous technological advancements and practical application in various industries.
So now, let's proceed to dispersion. It is the splitting of white lights into its constituent colors. Like when you see a rainbow, it uses a in prism and spectrometers, which can analyze the chemical compensation of substances by looking at the light they emit or absorb. So dispersion, illustrated vividly in natural phenomena like rainbows, involve the separation of white light into its component colors when passing through a medium, with verifying refractive indices. An example for this is prism, where different wavelengths or light are refracted by different amounts, resulting in a spectrum of colors. Spectrometers employ this principle for chemical analysis. For instance, when a substance is illuminated, it emits or absorbs light at specific wavelengths, creating a unique spectral pattern. By dispersing and examining this light using a spectrometer, scientists can identify the substance's chemical composition. An example is using a spectrometer to analyze the absorption lines in the star spectrum, revealing the elements present in the star atmosphere. So now, let's proceed to polarization. It is when light waves are restricted to a single plane. Polarization is used in many areas, including reducing glare in the sunglasses and improving the picture LCD TVs. It also used in some scientific and industrial applications, like studying molecular structures and the stress analysis in transparent materials. So we all know that polarization refers to the alignment of light waves in a specific plane. Light waves usually oscillate in various directions, but when you polarize, they vibrate predominantly in one plane. This properly finds application in diverse fields. For instance, in sunglasses, a polarizing filters selective blacks horizontally polarized light, reducing glare from the reflective surfaces such as water or woods. In LCD TVs, liquid crystal molecules are manipulated to control the polarization of light, enhancing image quality. In scientific endeavors, polarization is employed to study molecular structures by analyzing how polarized light interact with the materials. Scientists can gain insight into molecular arrangements. Additionally, polarization is utilized in stress analysis for transparent materials, revealing stress patterns based on changes in light polarization.